In this video, we're going to learn about conjugate acid-base pairs. So let's take a look at this reaction. On the left side, we have HF and H2O, and on the right side, we've got fluoride and hydronium. This reaction has equilibrium arrows because it's not something that 100% goes forward or 100% stays on the left side. It's something where there's an equilibrium between the two. So what we can say is that if we're looking at the left side, there's going to be an acid here, and there's going to be a base. And as I look here, HF, well, you may already recognize it as an acid. So I'm going to label it as such. And I'm going to label the water as a base because it has to be in this reaction. But notice, my acid, when we go to the other side, it has lost an H+. So what I can say is that the HF is transferring an H+ over to the base. That's really the definition of Bronsted-Lowry acids and bases, is what is losing the H+ and what's picking it up. And notice my HF as an acid becomes F-, which absolutely is not an acid at this point because it has no H+ to lose. It actually is somewhat basic at this point. And so I'm going to label this my conjugate base. And what's interesting is that my H2O, which was definitely basic in the context that we had here, right? With HF, the H2O has to act as a base. But now once we get over here, we look at it and it's like, well, H3O+, that's not going to act as a base. That's not going to become H4O positive 2. But what it can do is it can lose an H+ and give it to the F- and bring us back in the opposite direction. And in doing so, the H3O+ would be acting as an acid. So we call this our conjugate acid. And what you want to do is just look at these pairs. We have the HF, the acid, becoming the F-, the conjugate base. And we've got the H2O, the base, becoming the H3O+, the conjugate acid. Let's talk about the strength of acidity and bases, or of acids and bases. We had an equilibrium in this case, and I didn't really signify what side was favored. In this case, it's fairly obvious because there's only one arrow here. It's only one arrowhead. It's saying straight forward. And this is because on the left side, we're starting with HCl, which you know to be a strong acid. And we're starting with water, which I guess has to be a base. What happens is the HCl will transfer an H+ to the H2O. And we end up with Cl-, which can't lose an H+. It's going to be our conjugate base. It has a negative charge. It's got electrons that it can use to pick up an H+. So actually, our H3O+ will be our conjugate acid, and it can give an H+ to the Cl-, except, well, this has the same anatomy of the previous. But why is it that in the previous case we have the double-headed arrows, and in this case we only have the one-headed arrow? Well, think about this. This isn't just any acid. This is a very strong acid. Very, very strong acid. This water is going to be a weak base. Our chloride anion is about as weak of a base as you're going to find. It's incredibly weak. So this is an incredibly weak base. And the acid, the conjugate acid, is still going to be a weaker acid than the HCl. So what we get to is that we have a weaker base relative to the initial base, and we have a weaker acid relative to the initial acid. And so equilibrium is going to favor this side. but it's going to favor this side pretty much to 100% because chloride is basically a non-base. And we're going to get into that, quantifying that in just a moment. Next, we have this example, and we have a weak acid. This is going to be CH3COH, which I suppose you also may see written as HC2H3O2. The H is out in front. Sometimes it's this H that's with the O's, that would be the acidic H. Also, I like to write it with the H out in front to signify it's an acid, just like with HCl. Anyway, there's that reacting with water, which is a base, and it is weak. And then we had a transfer of an H plus to the water from the acid. This is actually vinegar, by the way. Our negatively charged conjugate base is this. And then we have our conjugate acid here. We know that there could be a transfer of H plus back. And actually, this reverse happens quite well. We can see that these are both weak, all right? But this acid is actually stronger than the acid on the other side. And this base may be a little bit stronger of a base than the water. And so we have equilibrium. It's not 100%, but the equilibrium actually does favor the left side. So how do we tell what is stronger and what's weaker? Well, we have all this stuff here. Let's break it down. So perchloric acid, sulfuric acid, hydrochloric nitric, these are strong acids. And they have a very large Ka, all right? If you look at what the definition of Ka is equal to the concentration of the products, which is going to be H3O plus, times the conjugate base of the acid, which, let's just use perchloric acid for an example. So the conjugate base is going to be ClO4 minus, over the starting material, the molecular acid, which is HClO4. This is for the, and it's concentrations of these. This is for the reaction of, we have HClO4 plus H2O, giving us H3O plus ClO4 minus. Now, depending on the year and the order in which we introduce things, you may be wondering why the H2O is omitted from this K. H2O is a liquid. Liquids are not involved in equilibrium expressions. Everything else is aqueous, so they are involved. If this means nothing to you, don't worry about it. Concentration of H3O plus and concentration of ClO4 minus, these are going to be very high. We have a lot of products over a very small amount of HClO4 that didn't dissociate, and that's why we have a very large value of Ka for this very strong acid. Now, if we had a weak acid, then we just wouldn't have a very large amount of H3O plus and conjugate base. We would have a very small amount of it and a whole lot of the non-dissociated molecular acid. And that would be the case with vinegar, C2H3O2, which we just looked at a moment ago. And so actually carbonic acid is an example of something that's pretty weak. It's actually stronger than vinegar, and yet we get 10 to the negative 7th as the quotient of essentially this, just with substitution of different conjugate base and molecular acid. I'll point out that substances that really do not dissociate into H3O plus and a conjugate base, they have an incredibly small Ka, and an example is hydrogen. Hydrogen is not really going to give you, H2 is not really going to give you H plus and H minus. It's not going to happen. And so you get a very low K value for that. By contrast, when we go over here to the right side and we look at the KB, this is essentially the exact opposite. Our perchlorate anion is not a base. It's a terrible, terrible base, which is why perchloric acid is so strong. The reverse reaction going from here back to the left is not going to happen with any appreciable degree. And so that's why the KB is so small. By contrast, if you had H minus and you mixed it with H plus, you would get absolutely 100%, you would get it to go to the left. And that's why the KB for hydride is very large. Have a good look at the relationship between an acid and its Ka, and then the conjugate base and its Kb. There will be very distinct relationships between them. So moving forward, one last thing, there's the concept of amphoterism, and this is the ability for something to act as an acid or a base. If you look at H2O, H2O can act as both an acid and a base. Where is water here? Water is right here. Okay, good. So notice our Ka for water is 10 to the negative 14th, and our Kb for hydroxide is 1. Well, when we have hydronium, where are we? The Ka for this is 1, just like the Kb for hydroxide is 1. And when we go to the conjugate base, H2O, the Kb, is 10 to the negative 14th. All this is saying, look, 10 to the negative 14th in both cases, when we're talking about water acting as an acid and as a base, what we're saying here is that water is no better at acting as an acid than it is as a base. So it's actually equally acidic and basic. And so when we look at water, H2O can react with HCl to produce H3O plus OH minus, but water can also react with, I'm going to say hydroxide, but you know what? Let's just make it even something more basic than hydroxide. Let's go for NH2 minus. And that will give us, and by the way, I'll point out that NH2 minus is right here with a very large Kb, the amide anion. It's going to give us NH3 plus OH minus. And I just realized I put an OH minus up here. I meant Cl minus. Sorry. So water can act as an acid, as a base, as in this first case, and it can act as an acid, as in this case, because it's transferring an H plus, right, to the NH2 minus. And in the previous case, when HCl is the acid, it's transferring the H plus to water. Additionally, HSO4 minus can go in both directions. We can have HSO4 minus react with H2O, and we can have the H2O pick up an H plus, and we get, I'll just draw the arrow right now, we get SO4 minus 2 and H3O plus. The equilibrium favors the left side a little bit, but if you had a stronger base, it would really favor the right side. If we used NH2 minus, it would favor the right. Now, we can also have HSO4 minus act as a base, although it is very reluctant to do so. If we want it to act as a base, because sulfuric acid, H2SO4, is such a strong acid, the equilibrium when this is reacting with water is really going to favor it staying like this and not going back to H2SO4. So I'm going to take my HSO4 and make it somewhat reasonable here that we can actually protonate this HSO4 minus. So what if we had HClO4? an even stronger acid? Well, in this case, there still would be equilibrium, but we would have H2SO4 plus ClO4 minus. And that's just caused by the HClO4 transferring an H plus. And yeah, you can get the reverse happening as well. In both of these cases, you could have the H plus cause this to go in reverse in both cases. But I just want to point out that amphoterism is a thing, that something can act, a lot of substances can act as both acids and bases. And really, it just depends on the context. Water is very amphoteric in the sense that it can act as an acid when exposed to a lot of bases, and it can act as a base when exposed to a lot of acids. HSO4 minus is definitely more acidic than it is basic. So if you want to get this to act as a base with any appreciable amount, then you're going to have to add a lot of really strong acid to make that happen. But if you add anything even slightly basic, you're going to get a pretty good amount of HSO4 minus being deprotonated to form SO4 negative too. Anyway, I hope this video has been helpful. Let me know if you have any comments or feedback in the comment section below. Thanks for watching.